Hey everyone, welcome to CafeQED. My name is Peter, and today let's talk about implicit differentiation. Alright, before we get into it, let me first provide some motivation as to why we need this kind of differentiation technique. Basically, any function that we work with can be categorized as one of these two types of functions, explicit functions and implicit functions. Explicit functions are functions that we are already quite familiar with, and they're functions such as these, where y can be explicitly represented as a function of x, or in other words, our y can be isolated from x. Whereas implicit functions are functions like these, where the y is not explicitly specified as a function of x. Or in other words, it basically means that the x and y are mixed in with each other when we write down the equation. But note that this is not to say we can't solve for y in terms of x, making it an explicit function. It could either be very difficult to do so, or it could even be impossible to solve for y in terms of x. But either way, for an implicit function, it just means that the y isn't isolated. Now, looking at these two categories of functions, notice that all of the differentiation rules that we've learned so far dealt with differentiating explicit functions, where we had a y equals or an f of x equals something. And now our goal for today is to be able to differentiate implicit functions. So in other words, we would like to find dy by dx when given an implicit function. Okay, so now let's talk about how to perform implicit differentiation. And it turns out that it's actually not too bad. It basically calls upon all of the rules of differentiation that we've learned so far. And I will leave a link to all of those videos in the description below in case you need to review something. But basically, it boils down to two steps. Step one is to differentiate both sides of our implicit function with respect to x. And I'm going to leave an asterisk on differentiate because there is a nuance in how we differentiate something about our implicit functions. And I'm going to talk about that once we get to the examples. And then step two is to solve or isolate for dy by dx. Okay, so now let's take a look at a few example problems because I think that's honestly the best way to learn how to do implicit differentiation. All right, for our first example, let's try to find the derivative of the equation of the circle that we saw a little bit earlier. So in other words, given x squared plus y squared equals 1, let's try to find dy by dx. And I'm going to leave the two steps that we need to follow up here in the top right-hand corner, just as an easy way for us to refer back to what we should be doing. Okay, so starting with step 1, let's differentiate both sides with respect to x. So that'll look like this. We have the derivative with respect to x of the left-hand side, so x squared plus y squared. And then we also have a derivative of the right-hand side. Okay, so now let's take each of these derivatives, and I'm going to work this problem out step by step so it's easier to follow along. Okay, so for the left-hand side, I see that I can distribute my derivative to each of the two terms. So I get the derivative with respect to x of x squared plus the derivative with respect to x of y squared. And on the right-hand side, we have the derivative of 1, which would just be 0. At this point, we see there's something interesting going on, right? We see that there is this derivative with respect to x of y squared, which we're not really sure how to do. So let's step aside to try to figure out how to evaluate this derivative. Turns out it's a chain rule. And the reason for this is because we're going to temporarily assume that y is a function of x. Okay, so now let's see how this all works out. So starting with our original problem, we would like to find the derivative with respect to x of y squared. And then since y is a function of x, I'm going to replace y with y of x. So this will be equal to the derivative of the term y of x squared. And now in this form, I think it's easier to see that we will be using the chain rule, right? Because remember, the chain rule is used to differentiate composite functions. And what we have here is indeed a composite function. We have y of x on the inside, and we're plugging that into this squared function. All right, so now with that said, let's apply the chain rule. So we get that this will be equal to, first, the derivative of the outer layer. So we're going to differentiate the power to give us 2 times something raised to the first power. And then the something is we leave the inside the same. So we plug y of x back into the inside. And then we multiply this by the derivative of the inside. Well, the derivative of y of x is just y prime of x. So now let's clean things up. So the first thing I'm going to do is I'm going to replace y of x with just y. So basically moving back to our original form. So this will be equal to 2 times y. And then y prime of x, that's also the same thing as dy dx, right? It's just the derivative of y with respect to x. So my second term becomes dy by dx. And this is our derivative of y squared with respect to x. And finally, before we move back to our original problem of differentiating the equation for the circle, notice the pattern that came up when we tried to differentiate y squared. The first term, this 2y, looks like we just took a regular derivative, but with respect to y, right? Y squared goes to 2y. And then we attach an extra term of multiplying by dy by dx. And it turns out that this is exactly the pattern that we need to follow whenever we need to differentiate any term with y in it when we're doing implicit differentiation. Okay, so now let's go back and finish off our problem. We now know how to evaluate both of our derivatives here, right? So we have that the derivative of x squared will be 2x, plus the derivative of y squared with respect to x will be 2y times dy by dx, and then this is equal to 0. And here we are now done with step 1. We're done with differentiating both sides with respect to x. And now let's move on to step 2, which is to isolate for dy by dx. And this part is just basically a bunch of algebra. And this is what we get for the derivative. So yeah, this is implicit differentiation. It's not too bad, right? Basically, we just use all of the differentiation rules that we've learned so far, except for this minor nuance where whenever we need to take a derivative of a term with y in it with respect to x, we first differentiate that term as if it's a derivative for y, so like a regular derivative, and then we multiply by dy by dx. Okay, let's try this again on a different example problem. Okay, for our second problem, let's try to find the derivative of this other implicit function that we saw a little bit earlier in this video. And just like before, we're going to follow the two main steps of implicit differentiation. So first of all, we're going to differentiate both sides with respect to x. So we have the derivative of y to the fourth plus xy squared is equal to the derivative with respect to x of x cubed minus x minus 1. Next, I'm going to distribute my derivatives to each of the terms on the left-hand side. From here, if you're feeling comfortable with implicit differentiation, you can basically just go through and differentiate all of your terms on the fly, essentially getting you to the end of step 1 in one step. But I'm still going to take things step by step for everyone who's watching this video. All right, on the left-hand side, I'm going to distribute my derivative through to each of the terms. So I get the derivative with respect to x of y to the fourth, and then plus the derivative with respect to x of xy squared. And then this will be equal to, well, on the right-hand side, this derivative has no y's in it. So I'm actually just going to go through and differentiate this term directly. So we're going to get 3x squared minus 1. Okay, so before we work out the two derivatives on the left-hand side, let's first pause and just think about how we're going to approach both of these. The first one, the derivative of y to the fourth, is going to be pretty straightforward, right? It's reminiscent of what we saw earlier, where we basically just differentiate as if it's a derivative for y, and then we multiply by dy by dx. And the second term here, this one's a little bit more interesting, right? Because we have a derivative of a term where x's and y's are mixed together. But can anyone spot what rule we're going to be using here? It's the product rule, right? Because we have a derivative of x times y squared. All right, so now with that said, let's go ahead and differentiate the left-hand side. Our first term, the derivative of y to the fourth, will become 4y cubed times dy by dx. And then plus the second term, let's expand out using the product rule. So we get that this will be the derivative of the first term times the second plus the first times the derivative of the second. And then this is going to be equal to 3x squared minus 1 on the right-hand side. We're now left with two derivatives that we have to work out, so let's go ahead and do that. Our first term will stay the same. And then this will be plus, I'm going to drop the parentheses, and then derivative of x is 1, so this leaves behind a y squared. And then plus x times, now the derivative with respect to x of y squared will be first 2y, because we differentiate like normal, and then we multiply by dy by dx. And this will be equal to 3x squared minus 1. Okay, so now we are done with step 1, right? We finished all of our derivatives, and now let's begin step 2, which is the process of solving or isolating for dy by dx. And since the rest of our work is purely algebra, I'm going to fast forward until I get to the solution. And this is what I get for the derivative. All right, I have one more problem for us to look at, and this one is going to be slightly different from these two that we've already seen. So let's get right to it. For our last problem, let's say we're given this function here, and we want to find the value of the derivative at the point 1, 1. And this shouldn't be too bad, right? We first find the derivative using implicit differentiation, and then we evaluate it at the point. And I do want to point out that this point 1, 1 was not just arbitrarily chosen. It is a point that actually does lie on the curve that's defined by this implicit function. And you can verify this by basically just plugging in and checking that you get something that's valid. Okay, but with minor details aside, let's go ahead and take the derivative of this implicit function. As usual, the first step will be to differentiate both sides with respect to x. So we get the derivative with respect to x of x over x squared minus y squared plus 1. And then the right-hand side is the derivative with respect to x of cosine of x minus y. Okay, so now let's pause and think about how we're going to approach the derivatives on either side. On the left-hand side, we have a derivative of a quotient, right? So this means that we're going to be using the quotient rule. And then on the right-hand side, we have a cosine of x minus 1. In other words, we have a composite function. So this means that we're going to be using the chain rule. Okay, so now let's expand out both the left and right-hand sides according to the rules that we've just figured out. On the left side, we're going to get low d high, which will be the derivative of x, minus high d low, which would be the derivative of x squared minus y squared plus 1. And then over the square of what's below, so we divide by the denominator squared. Okay, so that was the quotient rule. And then the right-hand side for the chain rule, we first differentiate the outer layer. So this will be the derivative of cosine, which is negative sine. And then we keep the inside the same. So we plug x minus y back inside. Then we multiply by the derivative with respect to x of the inside. So the derivative of x minus y. All right, and now let's work out each of these smaller derivatives that popped up when we use the quotient and the chain rule. On the left-hand side, we're going to get x squared minus y squared plus 1 times 1, that's the derivative of x, minus x times the derivative of x squared, which will be 2x, minus the derivative of y squared will be 2y times dy dx, and then plus 0, that's the derivative of 1. And then all of this, again, will be over x squared minus y squared plus 1 all squared. And then the right-hand side, this will be negative sine times x minus y, and times the derivative of x is 1, and then the derivative of y is, well, dy dx. And the reason why is because the derivative of y is just y prime, which is just dy dx. Okay, so now we're done with step 1. We've taken all our derivatives. And now for step 2, we need to solve or isolate for dy by dx. But looking at this seems like a lot of work to do, right? We need to multiply things around, we need to distribute things, we then, just too much stuff going on. And for some problems, we might actually have to just go through all of that work to figure out dy by dx. But fortunately for this particular problem, we can actually skip a lot of that messy work. And the reason why is because of what I'm asking for us to find. So looking back at the original problem, I want us to find the value of the derivative at the point 1, 1. And what I take from this is that I'm not necessarily looking for an expression for dy by dx. All I need to know is the value of dy by dx. So this means that for us, we don't need to isolate for dy by dx to find the expression. We can actually just go ahead and first plug in 1, 1, and then figure out the value of dy by dx. And this should be a little bit easier, right? Because instead of carrying around our symbols of x and y and all these terms, we can just simplify everything down to numbers because we're plugging in 1, 1. All right, so let's do that. So on the left-hand side, we're going to get 1 squared minus 1 squared plus 1, then minus 1 times 2 times 1 minus 2 times 1, and then this is going to be times dy by dx, because remember, we're looking for dy by dx, so we can't be plugging anything into dy by dx. And then divide this by 1 squared minus 1 squared plus 1, all squared. And then the right-hand side, we're going to get negative sine of 1 minus 1 times 1 minus, and again, we can't plug anything into dy by dx, so that stays as that. Okay, so from here on out, until we get to dy by dx, it's all just going to be algebra. So let's meet back up again once I get to the solution. And we get that the derivative of our implicit function at the point 1, 1 is equal to 1/2. So there are two things that I wanted to demonstrate with this problem here. The first one is that we can mix all of the rules that we've seen so far into any problem involving implicit differentiation, right? We saw both the quotient rule and the chain rule used in this problem. And secondly, I wanted to show you guys the shortcut that we can take if our eventual goal of implicit differentiation is to evaluate the derivative at a point. And what we saw here was that we can essentially skip the process of isolating for dy by dx to figure out the expression for the derivative. And this is potentially great because that algebraic work could be rather difficult. And instead of doing all of that, we first plug in the point that we would have eventually evaluated our derivative at anyway, and then simplify with only numbers left in our expression. All right, before I finish off this video, let me just quickly go back and add in the minor detail that I left out when I first introduced the two steps for implicit differentiation. So the first step that we're now familiar with is to differentiate both sides of our implicit function with respect to x. And the asterisk that I included earlier was basically to point out that anytime we need to take a derivative of an expression for y, we first differentiate like normal, and then we multiply by dy by dx. And for example, the derivative with respect to x of y squared is going to be 2y, and then times dy by dx. And then finally, step 2 is to solve or isolate for dy by dx. Alright, so that's all I have for today. If you have any questions, leave a comment below. If you enjoyed this video or found this video helpful, give it a thumbs up. And if you'd like to learn more math with me at CafeQED, hit the subscribe button. And I'll see you all next time.